Okay, we are going to start in on section 3.1. Oops, get the right size there. So we'll say 3.1. And so to begin, first of all, we're going to look at the slope of a secant line through 2 points of a function f. So we're going to look at delta f over delta x. And we're going to note that this is going to equal f of x minus f of a, all that over x minus a. And so this right here should note this represents the slope of a secant line through the point a f of a and x f of x. And it is also the average rate of change. So if we draw a picture of this, say pretend we have a better line. Say we got that, and let's just say we have some function that kind of curves upwards. So we could say our point A is here. The corresponding y value for that point we could say would be f of a. And we're looking some distance out here to x. And so this distance out here would have a corresponding y value of f of x. Now, in this distance from here to here would be called delta f. And the distance from here to here we would call delta x. So between these 2 points we could draw a line. Let's see if we can draw a nice straight line that passes through both those points. Good enough. And so this line that we draw here, the slope of this secant line is this right here. So this average rate of change is the slope of the secant line. So we're kind of remembering this equation from back in section 2.1. Now what we're going to do next is kind of talk about how does this relate to the slope of a tangent line. So if we draw another picture down here, say we got our same curve, we got our point A, it has a corresponding y value of f of a, and we want to look at the tangent value that kind of just skims the graph once. I guess we could try green color, see if that works. Not quite too good. Too far back. There we go. It's probably about as good of a tangent line as we're going to be able to get here. So the slope of the tangent line, here's our tangent line. The slope of the tangent line if we remember from back in section 2.1, this is equal to the instantaneous rate of change instead of the average rate of change. And the instantaneous rate of change, we should say at x equals a, because that's where the, at x equals a is where the tangent line is skimming the graph. So we want to see how these two are related. And if you remember back in section 2.1, we took smaller and smaller intervals. So we looked at a to a value a little bit beyond and then made it even smaller and smaller and smaller. Basically what we're doing is we're taking the x and we're sliding the x closer and closer and closer over towards the a. So we could say we're looking at the limit as x approaches a, and the limit of these types of things, these secant lines, the limit of these secant lines as x approaches a is the slope of the tangent line. So if we look at the slope of the secant lines, we let x approach a, that becomes the slope of the tangent line. So we're going to give that a name. We're going to call that the derivative and give it the little symbol f prime. So from this, we could say f prime of a, which is going to be the slope of the tangent line, That'll represent the slope of the tangent line. It's also the instantaneous rate of change. At x equals a. So this statement here, this symbol here represents both of those things because those two things are equal. This will equal the limit as x approaches a of f of x minus f of a, all that over x minus a. And this will let us calculate the definition of a derivative. So basically what we're doing is we're taking the average rates of change, we're letting the x slide close to a, and then those average rates of change, which are the slope of the secant lines, will approach and will become the slope of the tangent line, which is the instantaneous rate of change. Another way we can kind of view this instantaneous rate of change or at least another way of viewing stuff is we could say, let's start out here at A, and let's go over a distance of h. So let's scoot over a distance of h, and then out here we would be at a plus h. So if we have our same type of curve, a is here, a plus h is up here. So a will correspond to the equation f of a, and when we move h units down, a plus h will correspond to f of a plus h. So if we wrote the slope of the secant line down, it would be f of a plus h minus f of a, that's the difference of the y's, f of a plus h minus f of a, all that over the further distance, a plus h, minus the closer one, a. And we'll see that the plus a and the minus a could cancel, and that'll give us the equation f of a plus h minus f of a, all that over the remaining h. And if we have stuff viewed this way, we want to let the a plus h slide closer to a, so we want to let the a plus h slide closer to a. And to do that, we need to let the h approach 0, because if the h gets smaller and smaller and smaller, then this will become closer and closer to a. So we'll put the limit as h approaches 0 out front of this, and then this is another way of calculating the instantaneous rate of change at a. Which is also slope of the secant line at A. So we have two different ways of kind of representing the same thing, and a lot of the kind of the differences is, do you call this point over here x, or do you call this point over here a plus h? They both lead to similar types of equations. And we're gonna kind of done with the setup of what we're doing. So we're kind of looking at average rates of change, limit as the bigger part slides towards the a, and then that limit, in this case its limit as h approaches 0, in this case its limit as x approaches a, that limit gives us the slope of the tangent line. And this statement here is called the derivative. So we'll write down the definition of the derivative and the tangent line, and then we'll work a couple examples that cover those, and then we have a few theorems and a few other examples.